With this, let's just review the procedure for writing a net cell reaction and how to calculate the potential from that. So basically, again, I'm just going to breeze through this. Write reduction half cells, and then it says here, and find the standard reduction potential for each in the appendix section. Again, we all know about this. Just multiply the half cell as necessary to match the number of electrons on both sides. And again, do not multiply the value of E when you're matching the number of electrons in the two half cells. So basically that's writing out the equation. Then write out the Nernst equation for this right hand cell, half cell. The right half cell is always the one which is attached to the positive potential, terminal of the potentiometer. And this is the E plus. Then write the Nernst equation for the other half cell, which is attached to the negative side of the potentiometer, and then calculate the net voltage on the two half cells. Pretty easy to do. And then from here, write the balanced equation of the two half cells, subtracting one from the other and obtaining the value of E. Pretty straightforward. So a concrete example, again, this is just review material. So in this one is a 0.5 molar concentration of silver nitrate with a 0.0 molar, 1 molar of cadmium nitrate at the other half cell. So the right half cell is silver getting reduced. Remember, all these reactions are written as though they were reduction reactions, even though we know that one of them has got to be the oxidation half cell. So when you write them out, is 2 silver getting 2 electrons to give you silver solid. And this is the potential associated with that. So clearly this is the oxidation, and that's the reduction. So we go E plus equals to the right hand cell, 0.0596 over 2 electrons transferred between them, 1 over, because silver is solid, so it's going to be 1 over the silver ion concentration squared, because we have 2 moles of that. Okay, and the other half cell is the same, 0.05916 over 2, but in this one again, also it's a solid divided by the cadmium ions in aqueous solution, which is 0.5, and that gives us a net potential of 0.781. So the Nernst equation, here we can go ahead and do the calculation, and eventually the cell potential comes out to be 1.2 times 1.242 volts. So this is how you write out the net cell reaction, and that's it. That's all that there is to it. This actually is material that we basically covered even in general chemistry. So, but just to review it, because we need to kind of keep reminding ourselves about how it's done. So let's go ahead and look at the intuitive way of thinking of the cell potentials. In this one, of course, it's always the electrons flow from the more negative terminal to the more positive terminal. So electrons in this particular case will flow from cadmium to silver, and the net potential harnessed in this cell is going to be the positive potential minus the negative potential. So this is 0.781 minus negative, makes it a very positive value of 1.242. So clearly the cadmium silver cell is even more has even more potential than the zinc copper cell that we saw earlier of which gives us 1.1 volts. So this is a pretty good cell that can actually be used for our batteries, because the higher the potential, the better. But there are other logistical reasons why you will not find this kind of cell in our ordinary batteries that we use for running our gadgets. So there are other things that build into it, but it's not just the question of the magnitude or the potential. There are other things which I'm not going to go into here. But anyway, finding the relative half cells. So in this case, it says here, when faced with drawing a cell from or a line diagram, I'm not going to go back into this. We've already done this. So you can actually go ahead and transform a line diagram into an actual equation for the 2 half cells. So I'm going to leave this for you to actually review. Nothing there that can be challenging, because I think we have exhaustively talked about that. Now let's talk about the standard electrode potential and the equilibrium constant, the relationship between the standard electrode potential and the equilibrium constant. So whenever you're talking about the concentration quotient, usually activities is assumed to be a value of 1 that we have already talked about. So the galvanic cells, the role of the galvanic cell, or the voltaic cell if you like, is to generate electricity, and it generates electricity until basically that particular battery dies. And so long as that particular cell has not reached equilibrium, it continues to generate that electricity that we harness for our purpose. So the sole purpose of a galvanic cell is to produce electricity, which we then harness in some kind of way. The potentiometer that we have to measure the current must be a high resistance device. Otherwise, if it allows a lot of current to pass through, the battery essentially dies within a very short period of time. So the potentiometer must have a very high resistance for it to be a workable device, right? So if you were to replace that potentiometer by a wire that is highly conductive, that would actually make that cell to reach equilibrium almost instantaneously. And of course, that would defeat the purpose of us having this particular voltaic cell working for us. So battery runs to 0 voltage very quickly. So this is a generic cell here, A moles of A plus N electrons. We've already done even with concrete examples of that. But this is just high, kind of emphasizing the application of the Nernst equation in that kind of way. And then we have how we go from E naught, how we obtain E naught, the standard reduction potential, from the equilibrium constant. Once you have found the value of K, using the relationship we talked about earlier, we can be able to calculate the standard reduction potential of that cell, because using this relationship, because 0.05916 over N log of K is going to be the standard reduction potential. But of course, we must always be careful to quote the temperature, because this value will be different at different temperatures. So now to calculate the value of K, because we know this, we can get this one readily from tables, right? So we can calculate the value of K using this relationship right here. 10 to the power NE naught over 0.05916. Again, this is material we covered in quant. So again, pretty review-like material. So this is a concrete example. And one thing that we see in an example such as this one, this is the typical silver copper cell that we talked about earlier. And you can see from a voltage difference of 0.46, because that's what this difference comes to, we have a very high value of K. So clearly the value of K itself again is a further measure of the drive of that particular potential. So a very high value of K means that we are harnessing quite a high voltage, at least at that particular moment that the difference was 0.46. Needless to say, that value does not stay at 0.46, and with time it continues to diminish, and as it diminishes, of course, the value of K correspondingly reduces in that kind of way. Okay. Does anybody remember this molecule, or a molecule like this? This is nickel glycine. And if you say it in quant, this would be one of those molecules that we saw that have got a capability of attaching themselves to metal ions. Okay. And that's in the complexation chemistry that we talked about. So here is your nickel right there in the middle, and you have these ligands, okay, that are attached to the nickel on both sides, that kind of way. And why are we looking at this? This is the basis of this kind of example that we actually also saw in quant. Now, here, the equilibrium constant K is also designated as beta 2, but basically the outline of the problem is just like we have talked about. So the whole thing about this is that eventually we can calculate the potential of that cell using this relationship we have just seen. And I'm not going to go into all this. You can actually review this at your own time. So we have 0.0596 over n log of K, and the K value is obtained here. We can calculate the value of the voltage, and the cell potential therefore comes to give us a negative 0.564 volts. So again, this is just an example of where you can integrate complexation with the value of the electrode potentials that are obtained as a result of that complexation reaction.